We're gonna miss half the class on the YouTube video. All right. Well, let's start the class for those on YouTube, talking about convergence. Yeah, so this, I believe I didn't record half of the class, but all right, let's talk about convergence. What do I mean by convergence? The idea is that as you refine the mesh, we kind of explained this a little bit when we were introducing the weak form, and I said that if you have the WX, depending on how your mesh becomes thinner and thinner, is basically if your weight functions become sharper and sharper, and then you should get more and more the strong form. This formally should be known as convergence, which means that as you reduce the element size and your weight functions become narrower and narrower, you should be getting closer and closer to the strong form. That's the idea of convergence. And these are just ways of defining. So when I say the finite element solution should be getting closer to the exact solution, how do I measure how close it is? Well, you integrate the error. So this is basically, if you think of norms of vectors, you basically square the elements, add them up together, and then take a square root. If you want to integrate, get the norm of a function, you basically square the function, integrate it, and take the square root. So this should be kind of taking the norm of a vector, but for a function. So what we are interested in is basically calculating the norm of the error. So the norm of the error is the difference between my finite element solution and the exact solution when I have it. Square that, integrate over the domain, and then take a square root. And then you can take a relative error. So if you scale that by the norm of the exact solution, you get a relative error. And the idea of convergence means, and skip that. Obviously, for many problems, we don't have an exact solution, but this is to show for a problem for which we do have the exact solution, that as we refine the mesh, we should be getting closer and closer and closer to that exact solution. And note that there's the exact solution for the displacements. So this is exact solution for displacements. And if you just take the derivative of that, this is the exact solution for the strains. This is the derivative of displacement. Here I'm plotting both the exact solution for I'm just plotting the equation there. This is the exact solution for the displacement, the exact solution for the strains. And then I'll skip this one. I'll come back to this in a sec. Do I have the plots? I don't have the plots. Oh, no. Wow. I guess I had it. I'll add a slide here before I post it because this must be in a different set of slides. But what does the finite element solution should look like? So if you only have a couple of points, then I think this might have been the one that I solved in PL3. So if you have two elements, it will look something like this. So it will look pretty good, even for two elements. The derivatives look pretty bad. So for the derivatives, because the derivatives are piecewise constant, that doesn't look very constant, but they are discontinuous, right? So the derivatives will be something like this for two elements. I'll replace this with the actual finite element solution because I did it for PL3. If you have more elements, so let's say you have, the solution that you get will basically pass through these points, and you can imagine that it will be closer to the exact solution. And as you add more and more elements, it gets closer and closer. The derivatives that one, because it's still piecewise constant, it will look something like that, where it will get closer, but it cannot get as close because for linear elements, the derivatives are always piecewise constant. So you will always get like little segments of line, but it will sort of follow that derivative. So the main idea of convergence is that if you increase the number of points to infinity, you will recover the exact solution. Obviously only valid in the infinity, but if you put a lot of points, your mesh has too many points, then you recover the strong form. Let's say not infinity, but a very large number, then you will really won't be able to tell the difference between the exact solution and your solution. And then for the derivatives, the same. Even though it will still be piecewise constant, it will get better and better. It will be discontinuous, but it will get better and better. That's the idea of convergence. This is what you were testing in your lab 3. So when now in this case, I actually have an exact solution, so I can compare and see what my error is. I can calculate the norm of the error and say, okay, I have a good solution or not. In many cases, like what you were doing in the lab 3, you also had an analytical expression for the stress concentration. In many cases, you don't have an exact solution, but you should still check for convergence. So what you should do is you should refine the mesh and then see how the solution changes. And then basically you want your solution to not change too much at a particular location of interest. So let's say you have your part and then you are interested in the stress at a particular region in your part because you think it's gonna fail at that location, then refine your mesh until the change of stress in that region changes very little. And so when that happens, that means that your mesh is fine enough to capture the change of stress in that region. And then even if you don't have an exact solution, then you know that your finite element mesh is converging to some value. So that's what you should try to do for any, especially if you don't have an exact solution. So you did it for lab 3, you had an exact solution for the stress concentration, so you could refine your mesh until you got to stress concentration that was similar to the analytical one. For cases where you don't have an exact solution, you should still refine your mesh and basically pick your location of interest where you have a larger variation of stress or where you expect the thing to fail, and then just monitor the stress at that location, and it will follow. If you pick the stress location of interest, you will see that as you refine your mesh, so as you make your mesh smaller, the stress at that location will start at some point. Let's say this is your coarse mesh, and this is your finest mesh. It will do something like this. So it's something that you should always do, especially if you don't have an analytical solution, you don't know if you are at the correct place, you should refine your mesh, and then basically you want to see, the change between these two, maybe like 10% change. So then it's probably not converged enough. Then if you check, the change there becomes smaller. So at some point it becomes very small. You can set a threshold, and then that's up to you. That's a little bit of a design choice. So you want to say, I want to refine my mesh until I get changes that are less than 5%, for example. So then you anticipate basically a 5% error. You can run multiple points and then try to fit a polynomial to that. And then what I can tell you is how fast, I'm gonna go back to the other plots. How fast is this convergence? So how fast is this? And that depends on the degree of polynomials that you use. So I'm gonna go back to these plots that look, oh, they are below. This type of plots show you the slope of these lines that compare the error to the element length. This is basically the order of convergence. You can see that these are log plots. So the slope here, so slope so what this tells you that the slope of for the linear elements, the slope for the displacement is quadratic. So that means that if you reduce the element size by half, you should improve your accuracy by 4 times. So the quadratic of that, if you use linear elements. Whereas for quadratic elements, it's cubic. The exponent is cubic. So that means that if you reduce the element size by half, your accuracy actually goes up by 8. That's for the displacement. And for the energy is basically stress or strain. Usually those have smaller convergence. So the convergence for the displacements is faster. So you get very quickly, very good at predicting the displacements. You don't get as good at predicting the stresses. So if you have linear elements, then you only get linear improvement on the stresses. So that means that if you decrease your element size by half, you get 4 times the accuracy on the displacement, but you only get 2 times the accuracy on the stresses. So that's what this exponent means for the linear elements. For the quadratic elements, again, if you decrease your element size by half, so you double your mesh size, then the accuracy on the displacements goes up by 8, but the accuracy on the stresses only goes up by 4. So the square. So this is just to give you an idea of how you should get more accurate. Again, what you should be doing, regardless of whether you use linear or quadratic elements, you should do this type of plot. If you are using linear elements, it will take longer to sort of get to the asymptote. If you use quadratic elements, it will very fast go to the asymptote. So it will just go. So let's say that this is with quadratic, and this is with linear. So you should monitor your stress at a particular location of interest. Again, if you're using linear, it will get to the converge value. Right? It will just take more refinement. If you use quadratic, it will more faster go to that converge value. Yes.
When you say linear versus quadratic elements, are you referring to the shape functions?
Yes, yes. Whether you use linear shape functions or quadratic shape functions. And so practically speaking, there's a trade-off, because as you can see, for the quadratic shape functions, you could argue why not just use quadratic shape functions from the start. And the trade-off is a couple of things. One is quadratic shape functions take more function evaluations because you have 3 shape functions per element. You cannot just use 2 Gauss points. You need to use 3 or 4 Gauss points to integrate them. So overall, you need to do much more computations. For linear elements, you need to do less computations. So what is best? Do you use the quadratic shape functions that you know converge faster? So with a slightly coarser mesh, you get better solution, but you need to do more computations, or you use the linear elements for which you know it converges much slower, so you need a finer mesh to get the solution, but the number of computations might be about the same for the quadratic. I would say a good rule of thumb would be to use quadratic elements is a good starting point. So quadratic elements is a good starting point for most problems. There are a few exceptions though, for which using linear might be more advantageous. So linear elements are good for problems with singularities. What do I mean by singularities? So when you have corners, if you have sharp corners, something like this, then that is, will have some stress concentration there. And then the problem is that when you have these type of singularities, even if you use quadratic elements, your convergence drops for this particular type of cases. So even if you're using quadratic elements, you get very slow convergence. Corner dominates convergence. So even using quadratic elements, you don't converge as fast. So you end up having really fine meshes anyways. So in that case, might as well use the linear ones. Another one is where you have excessive distortion. I don't know how to spell, but so when you have excessive distortion of elements, then also that reduces your convergence. It's just the elements, the shape functions are not as well behaved when you have a lot of distortion of elements. I know this is for like, in 1D, there's no distortion because things are just stretched. But in 2D, you can see elements that get really distorted. And then that reduces your accuracy. So then again, you kind of lose some of the power that you have with the quadratic elements if your elements get too distorted. Some rules of thumb. But the bottom line is you should refine your mesh and monitor the stress at locations of interest to make sure that it's not changing. Questions? Yes.
Does Abacus use quadratic elements as a default?
I actually don't know. I think the default is probably, but okay, it's in the next slide. Is it quadratic by default? I think that maybe the default is linear with reduced integration, which are the cheapest possible elements. So Abacus default is sort of the cheapest one, which is not bad. But the problem is that's why you need to do this convergence analysis, because with that element, you will see the next slide is the beam bending.
Yes.
Yeah, so you will see that with the cheapest element, which has the linear with reduced integration, you can get just terrible solutions for particular problems. So we'll do the beam bending, and you'll see the beam will just bend excessively, and it's just not physical. And then if you see what's going on, it's just that you don't have enough elements. If you were to refine, I don't know how many elements you need. You need a lot of elements of the cheapest one, which is the linear with reduced integration. Which works. I mean, all of them work. It's just a matter of how much do you need to refine your mesh to get them to work. So if you're using the cheapest one, you might just need to refine a lot. So that's the trade-off. All right, well, that's it. I guess I just did I did not start the 2D. We'll start on Wednesday for the 2D stuff, but I wanted to talk about convergence. So I'll see you on Wednesday.
Can you read the lab 2 report and not read the lab 1 resolution? But you didn't publish lab 2 report. I think it's waiting for you to look at it, maybe publish it.
Wait, let me stop recording.